So in this present context, we are dealing with the aspect of a launching of a satellite, or rather we can say Earth satellite system. So we are dealing with EARTH, Earth satellite system. So in order to understand this concept, we are taking the following things into consideration. So I'm mentioning a list of things which we are considering over here. So the first thing that I'm doing is I'm making Earth. So this is the Earth which we have, and we will be talking with respect to this the center of the Earth. The next thing which I specify is the region of the gravitational field of the Earth. So let us say that the Earth's gravitational field extend up to this larger circle, where the influence of the Earth's gravitational field will be felt, maybe a little feeble, but the extent is still this particular region. The next which I consider is the region where we will be discussing about our present scenario, that is the current context. So let us say we are discussing about our current scenario over here in a circular path which is say at a height h above the surface of Earth. So over here, if I start specifying the notations which we are using, so I'm saying that capital M be the mass of Earth, small m be the mass of satellite, capital R be the radius of Earth, h be the height of satellite from Earth, height of satellite from Earth. And over here I can say, I can add a very interesting fact over here, that small r is going to be r plus h. This is distance from the center of the Earth, distance from the center of Earth. V naught be the velocity of satellite, the translational velocity of the satellite. So these are the aspects which we are considering over here. So the mass of Earth is m, radius of Earth is r. It is at a height h above the surface of the Earth, and the planet is moving in this particular path with a velocity v naught. The light green circle, or the region which I have marked, is the region where the Earth's gravitational influence nullifies itself. So over here, the first thing which I wish to say is the equilibrium of the satellite. So when the satellite is at a certain height above the surface of the Earth, there is a gravitational pull which is acting between the satellite and the Earth. And to counterbalance this gravitational pull, force which is mv square by r will be acting away from the center of the circular path to balance the gravitational pull. So the first aspect which I write over here is for the equilibrium of satellite. So we are writing for the equilibrium of satellite. So over here I can say that the gravitational force is balanced by the centrifugal force. So over here we can say G mm upon r square is equal to the mass of the satellite m v square upon r. So this is the thing which we have written, and it should be noted over here that a small r is the distance from the center of the Earth which we are measuring. So over here I can get an expression for V naught. So V naught over here is turning out to be G capital M upon small r square root. So we are putting this in a bracket, and I can refer this as equation number 1. So now if the satellite is moving with this particular velocity, so the next thing which I do over here is I modify this particular expression. So I'm writing a note. So I can write that V naught can be written as G capital M upon capital R plus small h square root, because small r is the distance from the center of the Earth. So over here I am writing if the satellite is very close to the center of the satellite is very close to the surface of earth, to the earth surface or the surface of earth. So over here I can say that r plus h is approximated to be equal to r. So if I take the usual aspects, that is if I take capital G as 6.67 into 10 to the power minus 11, the mass of earth in the usual way, and the radius of earth is 6,400 kilometer, or I can modify this expression in this way: gm by r is square root. So if I multiply and divide by r over here, so we will get this expression as gm by r square, that is small g into capital R. So small g can be taken as 9.8 and capital R is 6,400 kilometer, which we convert into meter, that is 10 to the power 3. And then we take the square root of this particular term. So we are on solving, we are getting a value that is 9.2 kilometer per second. So this is the orbital velocity of the satellite, which is going to be if that satellite is very close to the center of the earth. So if that satellite is very close to the center of the earth, then that satellite must maintain a speed which is somewhat equal to 8 kilometer per second, which is 8,000 meter per second, so that it can move in a circular path around the earth, moving at a very close distance from the center, from the earth's surface. So this is the very first aspect that we have discussed over here. The next thing which we are going to discuss over here is the time period of the satellite. So the next thing which we are discussing is the time period of the satellite. So we are considering that the satellite is moving in a circular path with this fixed velocity v naught, which we have calculated as gm upon small r. So if it is so, so I can say that the speed of this satellite can be written as distance traveled upon time taken. So from here I can write, we are mentioning capital T. So the time taken over here can be written as 2 pi small r by v naught. So it can be written as 2 pi small r by v naught, and that is, it will be written as 2 pi small r, and v naught can be written as root over gm upon r. So from here I can write that t equals 2 pi by root over capital Gm into r to the power. So this square root r will go on top, so it will become r to the power 3 by 2. So r to the power 1, and then 3 will become r to the power 3 by 2. And this is a very interesting result that we have. This is in accordance with Kepler's law, as I can see that t square is proportional to r cube. So this is in accordance with the Kepler's law, where we studied that the square of the time period of revolution of a planet around the sun is a cube of the length of the semi-major axis. So over here the satellite is also following this basic rule. And over here, if I modify this expression in terms of height, so I can say that t equals 2 pi by root over gm, and this small r can be written as h plus r to the power 3 by 2. So this is going to be the expression for the time period of the satellite, which is moving at a height h above the surface of the earth. Now we are going to discuss the other aspect, that is we are going to discuss the energy profile of the satellite. So we are going to the another aspect where we are discussing the energy profile of the satellite. So we are discussing energy profile of the satellite. So when we talk about energy, we will be discussing the three basic aspects, that is potential energy, kinetic energy, and the total energy of the satellite. So the first thing that we begin with is the concept of the potential energy. So potential energy U can be written as minus G capital M small m upon small r, that is r plus h. The value of potential energy is going to be negative because the force is attractive in nature, and I've mentioned it while teaching you potential and potential energy, how we write the value of potential energy. So we are writing it as minus G mass of earth, mass of the satellite upon r plus h. The next thing that we write is the kinetic energy of the satellite, which is written as half m v naught square. So if I write this value, so v naught square will become gm by small r. So it can be written as half of small m g capital M by small r, which is written as r plus h. So over here we can clearly see that the kinetic energy value is turning out to be g capital M small m upon twice of r plus h, and it is a positive value. And it is a positive value. Over here I can say it is a minus of twice the potential energy value. So if I calculate the total energy, so then total energy is the sum of potential energy plus kinetic energy. So the total energy of the Earth satellite system is going to become minus of g capital M small m upon twice of r plus h. So if I add the values of potential energy and kinetic energy, we are going to attain this expression. So this is the potential energy, this is kinetic energy, and this is the total energy which we have for the energy profile of the satellite. And a very interesting note can be deduced from here as well. So this note is also applicable for what you say, for the electron moving in around the nucleus having atomic number z, and this equation is also deduced in Bohr model. That is, we write over here that total energy is equal to minus of kinetic energy is equal to potential energy by 2. This equation, this type of a equation also pop up in Bohr model. In Bohr model also we get the same expression that total energy is equal to minus kinetic energy, which is equal to potential energy divided by 2. Very interesting point over here is the value of total energy is negative. The value of total energy of Earth satellite system is negative. Of Earth satellite system is negative. It is also regarded as binding energy. It is also regarded as binding energy. So when I say binding energy, I mean to say that if I supply this energy to the satellite, then it will escape to infinity. So if you supply this energy to the satellite, then it will escape to infinity. The negative value is symbolizing that the satellite is bound to be near the surface of the Earth. If somehow by an external agent or any other source, if this energy is available to the satellite, then the satellite will escape to infinity. That is, it will go beyond the gravitational field of the surface of the Earth. So it will leave the Earth's influence and will escape to infinity if this energy is provided to it, and it is referred as a binding energy value. The next and the last category over here which we are going to discuss about is regarded as geostationary or geosynchronous satellite. So we are discussing the concept of geostationary or geosynchronous satellite. They can also be regarded as spy satellite. So geostationary or geosynchronous satellite is something we are discussing over here. So if I begin my approach over here to discuss the aspect of geostationary or geosynchronous satellite, let us understand the concept. So over here, when I talk about the satellite moving around the Earth, I mean to say that the satellite is moving around the Earth in this way. That is, Earth is also rotating and the satellite is also moving with a certain orbital speed. And I already mentioned over here that all orbital speed and escape velocity are two different aspects. It should not be confused with each other. We are seeing one particular case of orbital speed where it is coming out to be 7.9 kilometer per second. And the previous day we read that the value of escape velocity is 11.2 kilometer per second. So when the satellite is moving around the Earth, which is also rotating, and if I want the satellite to stay at rest relative to the Earth's surface, then it is important that the time period of satellite must also be 24 hours. Then only it will be possible that the satellite will be able to keep a watch at one particular place throughout the time. throughout the time, this kind of a satellite is regarded as geostationary or geosynchronous satellite. So over here I mention it in this way. If a satellite is at rest with respect to the earth, then it is regarded as geostationary or geosynchronous satellite or geosynchronous satellite. So over here I can say one basic aspect over here, that for a geosynchronous satellite or a geostationary satellite, the time period must be 24 hours, which is 86400 second. So the time period of the geostationary or geosynchronous satellite must be 24 hours or 86400 second. So if I come back to this particular equation that we have, the t equals 2 pi root over gm h plus r to the power 3 by 2. So I'm writing over here that same expression. So I write from t equals 2 pi root over gm r plus h to the power 3 by 2. So I'm just cross checking if we are written the correct equation. 2 pi by root over gm h plus r to the power 3 by 2. So correct. So over here I can say if I square both sides, so we will have a t square is equal to 4 pi square by gm r plus h cube. So from here I can write it in this way: t square into gm upon 4 pi square is equal to r plus h cube. So if I take a cube root on both sides, then I will write r plus h is equal to gmt square upon 4 pi square in cube root. And from here I get that h is equal to gmt square upon 4 pi square to the power 1 by 3 minus r. So from this particular expression, we can calculate the height of the geostationary satellite, that is the height at which this particular satellite must be launched, to establish that the time period of the satellite is restricted to 24 hours. So if I put over there capital G as 6.67 10 to the power minus 11, and the other parameters over here, 4 pi square t is 24 hours, a radius of earth is known as 6400 kilometers. So over here we end up getting that the value of h is turning out to be 3.6 into 10 to the power of 7 meter, or it can also be written as 36,000 kilometer. So if a satellite is at a height of 36,000 kilometer, then it will behave like a geostationary or a geosynchronous satellite. So these are the aspects which must be kept in mind when we talk about the Earth satellite system. So with this, we have come to an end of this wonderful chapter where we have discussed every aspect about the gravitational effect of Earth, the Newton's law of gravitation, the concept of potential energy and the field, followed by Kepler's law, and then the Earth satellite system.